What if I told you that everything you think you understand about speed is wrong? That the fastest thing in existence isn't just fast, it's fundamentally different from anything else. 299,792,458 meters per second. That's the speed of light. You've heard this number before. Maybe you've even memorized it, but do you actually understand what it means? Most people don't. They know light is fast. They know nothing can go faster. They might even know Einstein had something to do with it. But that's where the understanding stops. That's just memorization, not comprehension. When you truly grasp why nothing can exceed the speed of light, when you understand what's actually preventing you from going faster, you realize something profound. The speed of light isn't a cosmic speed limit slapped onto the universe like a traffic law. It's the universe itself. It's the foundation upon which reality is built. I'm going to show you exactly what that means. And we're going to start somewhere you might not expect, with falling objects and the moon. Pick up a ball, drop it, it falls. Simple, right? Obvious, but how fast does it fall? Galileo figured this out centuries ago. In the first second of falling, an object drops about 4.9 meters. That's on Earth's surface at sea level. Drop anything a feather in a vacuum, a hammer, a bowling ball, and it falls at the same rate, 4.9 meters in 1 second. Now look up at the night sky, find the moon. It's up there, orbiting Earth, going around and around. It doesn't fall, except it does. It's constantly falling, every single moment. The moon is falling toward Earth. Wait, you might say. The moon isn't falling. It's orbiting. Those are different things. No, they're the same thing. An orbit is just falling sideways fast enough that you keep missing what you're falling toward. The moon is moving tangentially, perpendicular to the direction of Earth's gravity. Gravity pulls it down, but because it's moving sideways, it keeps missing Earth. It falls around us. Isaac Newton understood this. And he had a brilliant idea. What if the force pulling objects down on Earth's surface is the same force keeping the moon in orbit? What if gravity extends all the way to the moon, but there's a problem? The moon is about 384,000 kilometers from Earth's center. We're standing on the surface about 6,400 kilometers from the center. The moon is roughly 60 times farther away than we are. If the same force affects both us and the moon, why doesn't the moon fall as fast as we do? Newton's answer: gravity weakens with distance. Specifically, it follows what we call an inverse square law. Double the distance and gravity becomes 1/4 as strong. Triple the distance, 1/9 as strong. The force decreases with the square of the dista. Hence, at the moon's distance 60 times farther than Earth's surface, gravity should be 60 squared times weaker. That's 3,600 times weaker. So, if an object on Earth falls 4.9 meters in 1 second, the moon should fall toward Earth by 4.9 divided by 3,600. That's about 1 point for millimeters. Did it match? Newton calculated the moon's orbital motion. How far does the moon fall toward Earth as it orbits? The answer: 1 point for millimeters per second squared. Exactly what his theory predicted. This was revolutionary. Newton took two completely unrelated observations, apples falling on Earth and the moon orbiting overhead, and showed they were the same phenomenon. One law, universal gravitation, explained both. This wasn't just correlation. This was prediction. This was understanding. Newton kept going. He calculated the paths planets should follow if gravity works this way. The math said ellipses. And what did astronomers observe? Ellipses. Johannes Kepler had already measured planetary orbits and found they were elliptical, but he didn't know why. Newton explained it with one elegant law. The tides made sense too. Why does the ocean rise twice a day instead of once if the moon just pulled Earth toward D itself? You'd expect one bulge of water on the side facing the moon. but there are two bulges, two high tides roughly every 12 hours. Here's why the moon doesn't pull uniformly on Earth. Water on the side of Earth closest to the moon is nearer than Earth's center, so it experiences stronger gravitational pull. Water on the far side is farther away, so it experiences weaker pull. The result: one bulge where water is pulled more strongly toward the moon, another bulge where water is left behind because Earth itself is pulled more than that distant water. Two tides, everything clicked into place. Why Earth is spherical? Gravity pulls everything inward equally. Why it bulges slightly at the equator? Rotation creates centrifugal effects that counterbalance gravity. Why O large cellist? Your bodies are round. Gravity shapes them. As measurements became more precise, scientists tested Newton's law more rigorously. They observed Jupiter's moons, Europa, Ganymede, Callisto orbiting the giant planet. With careful observation over months and years, they could check whether these moons followed Newton's predictions. They didn't, not quite. The moons appeared to be about 16 minutes ahead of schedule when Jupiter was closest to Earth, and 16 minutes behind when Jupiter was farthest away. This was a massive discrepancy, had Newton been wrong. Rachmer, a Danish astronomer, noticed something crucial. The moons were ahead of schedule when Jupiter was near Earth, behind schedule when Jupiter was far. The discrepancy correlated with Earth-Jupiter distance. Rachmer had confidence in Newton's gravitational law, so he proposed something radical. Light takes time to travel. When we see Jupiter's moons, we're not seeing them as they are now, but as they were when the light left them. When Jupiter is closer, light arrives sooner. When Jupiter is farther, light takes longer to reach us. The moons weren't off schedule, our observations were delayed by light's travel time by measuring. This timing difference, Rachmer calculated light's velocity. This was the first demonstration that light doesn't travel instantaneously. It is a finite speed. Think about what just happened. We discovered the speed of light not by directly measuring light, but by trusting Newton's law of gravity. When observations didn't match predictions, instead of abandoning the theory, Rachmer asked, what else could explain this, and he found the answer. This illustrates something profound about science. When you understand one law deeply, it becomes a tool to discover others. Each discovery enables more discoveries. This process has accelerated for centuries, an avalanche of knowledge building on itself. And we're still in the middle of that avalanche. Once you know light has a finite speed, once you start measuring it carefully, you notice something bizarre. Light always travels at the same speed, always 299,792,458 meters per second. No matter who measures it, no matter how fast the measurer is moving. Let me make this concrete. Imagine you're standing still in space. You turn on a flashlight. You measure the light's speed as it leaves the flashlight. You get 299,792,458 meters per second. Perfect. Now you get on a spacecraft. This spacecraft is moving at half the speed of light, about 150 million meters per second. You point your flashlight forward in the direction of travel. Common sense says the light should now be moving at its normal speed plus the spacecraft's speed. Just like if you throw a baseball forward from a moving car, the baseball moves faster relative to the ground than if you threw it while standing still. You measure the light. What do you get? 299,792,458 meters per second. The exact same speed as before. The spacecraft's motion didn't add to the light's speed at all. Maybe I made an error, you think, so you accelerate the spacecraft to 90% the speed of light. You shine the flashlight forward again, you measure, still 299,792,458 meters per second. You push harder, you get the spacecraft to 99.99% the speed of light. You're moving so fast that everything outside is compressed by relativistic effects. You shine the flashlight. You measure 299,792,458 meters per second. Unchanged, this should violate everything you know about motion. Velocities add. If you're walking forward on a train, your speed relative to the ground is your walking. G speed plus the train's speed. But light doesn't work this way. Light's speed is absolute. It's the same for everyone, regardless of their motion. Why? What's going on? Albert Einstein solved this puzzle in 1905 with his theory of special relativity. His solution is so counterintuitive, so alien to everyday experience, that even today people struggle to accept it. Here's what Einstein realized. Space and time are not fixed, absolute things. They're flexible. They change depending on your motion. When you move faster, time literally slows down for you. Your watch ticks slower. Your heartbeat slows. Every physical process in your reference frame runs slower compared to someone who's stationary. This isn't an illusion. It's not a measurement error. Time actually passes more slowly. Let me give you a concrete example. Imagine twins. One stays on Earth, the other boards a spacecraft and travels at 99% the speed of light to a distant star and back. The journey takes 10 years according to the twin on Earth, but when the traveling twin returns, they've only aged about 1 point for years. They're now 8.5 years younger than their twin. This isn't science fiction. This is how time actually works. The traveling twin didn't feel time moving slower. From their perspective, everything seemed normal. Their heart beat normally, their watch ticked normally. But compared to the stationary twin, less time passed. This is the twin paradox, though it's not really a paradox once you understand that time is relative. Simultaneously, distances contract in your direction of motion. The space in front of you compresses. If you're traveling at 90% the speed of light toward a star that's 10 light years away, that distance contracts to about 4.4 light years in your reference frame. The star appears closer to you because space itself has compressed. This creates a fascinating symmetry. From Earth's perspective, your clock runs slow and you take longer to reach the star. From your perspective, the distance to the star is shorter, so even though your clock runs normally, you cover less distance. Either way, the math works out. The speed of light remains constant. These effects, time dilation and length contraction, are precisely calibrated to keep light speed constant. When you're moving fast and you measure light, your slow time and contracted space combine in exactly the right way to make light appear to be traveling at 299,792,458 meters per second. Think about how radical this is. For thousands of years, humans assumed time flows uniformly for everyone. 1 second for you is 1 second for me. Newton built his entire system of mechanics on absolute time. Einstein showed this is wrong. Time is personal. Your time is not my time. They're related, but they're not the same. The universe literally warps space and time to ensure light always travels at the same speed for every observer. This is not a force acting on space and time. This is the nature of space and time themselves. They are fundamentally flexible, dynamic, responsive to motion. Let me say that differently. The speed of light isn't just a velocity. It's a fundamental structural property of spacetime itself. The universe is built in such a way that this speed is invariant, the same for everyone, always. It's the one fixed point in a universe where almost everything else is relative. Now we come to the central question: why can't anything go faster than light? Here's what happens when you try to accelerate an object. At low speeds, everything behaves normally. You apply a force, the object accelerates, double the force, double the acceleration. Simple Newtonian mechanics: push a shopping cart twice as hard, it accelerates twice as fast. But as you approach the speed of light, something strange happens. The object starts resisting acceleration more and more. It's not that your engine is weak. It's not friction or air resistance. The object itself becomes harder to accelerate. Imagine you're in a spacecraft accelerating toward the speed of light. At first, everything seems normal. You accelerate smoothly. But as you get to 50% of light speed, you notice something odd. You're burning the same amount of fuel, applying the same force, but your acceleration is decreasing. You're not speeding up as fast as you were before. You push harder, more fuel, more thrust, you get to 90% of light speed. Now the problem is severe. You're applying enormous force, but your acceleration has dropped to a tiny fraction of what it was at the start. You're barely gaining speed despite pouring energy into propulsion. You don't give up. Maximum thrust, everything the engines can produce. You inch closer, 99%, 99.9%, 99.99%. But no matter how much energy you add, you can't reach 100%. The spacecraft's resistance to acceleration approaches infinity as you approach light speed. We describe this as relativistic mass increase, though that terminology is somewhat outdated. What's really happening is that the object's inertia increases. As you approach light speed, the object's resistance to acceleration approaches infinity. To accelerate an object with mass to the speed of light would require infinite energy, not just a lot of energy, not more energy than exists in the universe, infinite energy, which is impossible. You could harness every star in every galaxy, and it still wouldn't be enough. Infinity is not a really big number. It's a fundamentally different category. So nothing with mass can reach the speed of light. Not because we lack the technology, not because we haven't figured out the right propulsion system, because the fundamental structure of spacetime prevents it. It's like trying to count to infinity. You can count higher and higher, but you'll never finish. You can accelerate closer and closer to light speed, but you'll never reach it. Light can travel at this speed because photons are massless. They have zero rest mass. Massless particles don't. Just travel at the speed of light they must. They have no choice. They always move at exactly that speed. Never faster, never slower. A photon is created moving at light speed and annihilated moving at light speed. It never accelerates, never decelerates, never rests. But anything with mass, no matter how tiny, can only approach the speed of light asymptotically. You can get to 99% of light speed. The energy you're adding contributes significantly to the object's mass, which makes it even harder to accelerate. You're trapped in a vicious cycle. You add energy to go faster, that energy becomes mass. More mass means more resistance to acceleration. So you add more energy, which becomes more mass, which requires more energy, and so on in an endless spiral that never quite reaches light speed. Why is the universe structured this way? Why is there a speed limit at all? Why did nature choose this particular value to 199,792,458 meters per second? Here's the answer: there isn't really a limit in the sense of a boundary imposed from outside. The speed of light is a consequence of how spacetime is geometrically structured. It's not an arbitrary rule, it's an inevitable feature of the way reality is built. Space and time aren't separate, independent things. They're woven together into a four-dimensional fabric we call spacetime. And spacetime has a geometry, a mathematical structure. That structure includes a built-in conversion factor between space and time. That conversion factor is the speed of light. Think about it this way. You measure space in meters, you measure time in seconds. These seem like completely different units, unrelated. But they're not. They're to aspects of the same thing, space-time. And there's a conversion factor between them, 299,792,458 meters per second. It's similar to how Fahrenheit and Celsius are different temperature scales with a conversion factor between them, or how kilometers and miles are different distance units that can be converted. D. Space and time are like that, except more fundamental. They're different directions through spacetime, and the speed of light is the conversion ratio. This isn't specific to light, it's a property of spacetime itself. Light happens to travel at this speed because photons are massless and must move at the maximum possible speed through spacetime. But if light didn't exist, the conversion factor would still be there. It would still be the maximum rate at which cause and effect can propagate through the universe. Imagine you're walking across a field. You can walk north or east or any combination. Your total speed is limited. You can only walk so fast. If you walk purely north, you're not going east at all. If you walk northeast, you're dividing your motion between north and east. The faster you go east, the slower you go north, and vice versa, because your total speed is fixed. Spacetime works similarly, except instead of north and east, it's time and space. And instead of your walking speed being the limit, it's the speed of light. Here's another way to understand it. In everyday life, you think you're sitting still right now, not moving through space, but you're not still. You're moving through spacetime at a constant rate. Always. Everyone is. But that motion is divided between movement through space and movement through time. If you're sitting still in space, all your motion through spacetime is directed through time. You're moving into the future at 1 second per second, maximum speed through time. You're aging at the fastest possible rate, experiencing time at its normal flow, but when you start moving through space, you divert some of that motion. You're now moving through both space and time, which means you're moving through time more slowly. Your clock ticks slower, you age slower. The faster you move through space, the slower you move through time. There's a limit to this trade-off. If you could move through space at the speed of light, you would have zero motion left for time. Time would stop completely for you. You would experience no passage of time whatsoever. This is why, from a photon's perspective, no time passes. A photon emitted from a distant star and absorbed by your eye experiences no time between emission and absorption. From its perspective, these events happen simultaneously. The photon's entire existence, from birth to death, is a single timeless instant. You can't go faster than light because you can't have negative motion through time. That's the wall. That's the absolute limit. Going faster than light would mean moving backward in time, which creates causality paradoxes and doesn't make physical sense in our universe. It would mean effects preceding causes, results coming before actions, a universe where logic breaks down. The speed of light is thus the speed of causality itself. It's the maximum rate at which one event can influence another. When you press a light switch, the electromagnetic signal travels down the wire at nearly the speed of light. The light bulb can't turn on instantaneously because the causal influence can't travel faster than light. This has profound implications. It means the universe has a structure to it, a causal structure. Events are organized into past, present, and future based on light cones. Your past light cone contains all events that could have influenced you. Your future light cone contains all events you could potentially influence. Everything outside your light cone is elsewhere, neither in your absolute past nor your absolute future. These are events that are space-like, separated from you, events that can't affect you and that you can't affect. This isn't just theory. We've tested it extensively in dozens of different ways. Particle accelerators push subatomic particles to incredible speeds. The Large Hadron Collider accelerates protons to 99.9999991% of the speed of light. And what happens as these particles approach light speed? They become harder and harder to accelerate, exactly as relativity predicts. We pump more and more energy in, and they get closer and closer to light speed, but they never quite reach it. The energy goes into increasing their relativistic mass instead of their velocity. GPS satellites orbit Earth at about 14,000 kilometers per hour. That's fast, but nowhere near light speed, yet even at this relatively modest velocity, time dilation is measurable. Time passes slightly faster for GPS satellites than for clocks on Earth's surface, both because they're moving and because they're in a weaker gravitational field. This difference is about 38 microseconds per day. That might not sound like much, but GPS works by timing radio signals. Light travels about 30 centimeters in a nanosecond. 38 microseconds is 38,000 nanoseconds. If we didn't correct for relativistic time dilation, GPS would accumulate errors of about 11 kilometers per day. It would be useless. Engineers account for time dilation when programming GPS satellites. This isn't theoretical physics in an ivory tower. This is practical engineering that you use every time you navigate with your phone. Cosmic rays bombard Earth constantly. When high-energy particles from space hit the upper atmosphere, they create showers of secondary particles, including muons. Muons are unstable particles with a half-life of about 2.2 microseconds. They decay quickly. The upper atmosphere is about 10 kilometers up. A muon moving at, say, 99.8% the speed of light would take about 33 microseconds to reach the ground, but with a half-life of 2.2 microseconds, most muons should decay long before reaching sea level. We should barely detect any muons at ground level, but we do. Lots of them. Why? Because the muons are moving so fast that time dilation is significant. From our perspective on the ground, the muons' clocks run slow, so they live longer and make it to the surface. From the muons' perspective, the distance to the ground is length. Contracted, so they have less distance to cover before they decay. Either way, relativity predicts we should detect many muons at sea level. And we do. The prediction matches observation perfectly. Atomic clocks are extraordinarily precise. In 1971, physicists took atomic clocks on airplane flights around the world, some flying eastward, some westward. When they compared these clocks to clocks that stayed on the ground, they found tiny differences. The flying clocks had experienced less time, exactly as relativity predicted, accounting for both their velocity and their altitude. Time dilation has been measured with clocks on mountains versus clocks at sea level. It's been measured in particle accelerators. It's been observed in the decay rates of unstable particles. It's been confirmed in GPS satellites, atomic clocks on airplanes, and cosmic ray showers. The speed of light being constant and being a universal speed limit is among the most well-tested principles in all of physics. It's not speculation, it's not philosophical music. It's measured, confirmed reality. Let's trace the thread of discovery that got us here. It started with Newton watching objects fall and looking up. At the moon, he realized gravity is universal. That insight let him predict planetary orbits, explain tides, and unify terrestrial and celestial mechanics. Rackmer trusted Newton's gravitational law so much that when Jupiter's moons didn't match predictions, he didn't abandon the theory. He looked for another explanation and discovered that light has a finite speed. Physicists measured light's speed. More and more precisely, they discovered it's always the same, regardless of the observer's motion. This violated common sense and Newtonian mechanics. Einstein took this bizarre observation seriously. He asked, what if light's speed is actually constant? What would that mean for space and time? His answer, space and time must be flexible, relative, unified into spacetime. From this, Einstein derived time dilation, length contraction, mass energy equivalency equals mc, and the impossibility of faster than light travel. All from one principle: the speed of light is constant. Then came the tests, particle accelerators, atomic clocks, GPS satellites, cosmic rays, gravitational time dilation. Every test confirmed relativity. Each discovery built on previous ones, each answer raised new quests. Ions, each breakthrough provided tools for further investigation. This is the avalanche of knowledge that's been building for centuries. And it's still accelerating. So, what is the speed of light, really? It's not just the speed at which light travels. It's the maximum rate at which information can propagate through the universe. It's the speed of causality. It's the speed at which now spreads. Outward from any event, when something happens, a star explodes, a signal is sent that information spreads outward at the speed of light, no faster. Events are separated by light cones. You can only affect things within your future light cone. You can only be affected by things within your past light cone. Everything outside your light cone is causally disconnected from you. The speed of light is also the speed at which all fundamental forces propagate. Gravity waves travel at the speed of light. Electromagnetic fields propagate at the speed of light. The strong and weak nuclear forces have even shorter ranges, but their mediating particles still respect the light speed limit. In a sense, the speed of light is the speed of reality itself. It's the rate at which the universe updates. It's built into the fabric of spacetime at the deepest level. This is why the speed of light is special. Not because light is special, though light is remarkable, but because spacetime itself has this fundamental property. The speed of light is simply our name for that property, named after the first massless particle we studied extensively. Here's what amazes me most. The universe doesn't owe us comprehensibility. It could have been chaotic, random, impossible to understand. Reality could have been an incomprehensible mess with no patterns, no laws, no logic, but it's not. It follows laws. Deep, mathematical, beautiful laws, and we can figure them out. We started by watching apples fall and the moon orbit. Simple observations that anyone could make. We ended up understanding the structure of spacetime itself. We went from things fall down to space and time are unified and flexible in a few centuries of careful observation, creative thinking, and rigorous testing. Think about the journey. Galileo drops objects and times their fall. Newton watches the moon and realizes it's falling too. Rackmer observes Jupiter's moons and discovers light has a speed. Physicists measure that speed precisely and find it's always the same. Einstein takes this seriously and discovers that space and time are relative. Experimentalists test his predictions and find them correct. Engineers use these effects to build GPS satellites that guide you to the grocery store. Every step builds on the previous ones. Every answer raises new questions. Every mystery solved reveals deeper mysteries, and yet, through it all, we keep making progress. We keep understanding more. The speed of light isn't just a number to memorize for a physics test. It's a window into how reality works. It reveals that space and time are not what they seem. It shows us that the universe is stranger, more subtle, more elegant than everyday experience suggests. Common sense says space is space and time is time. They're different, separate, independent. Common sense is wrong. They're unified. They're aspects of the same thing. And that thing, space-time, has properties that determine what's possible and what's not. Common sense says if you're moving and you throw something forward, it goes faster. Common sense is wrong. Light doesn't work that way. The speed of light is absolute, invariant, the same for everyone. Common sense says time passes at the same rate for everyone. Common sense is wrong. Time is relative. Your time is not my time. We discovered all this not by trusting our intuitions, but by questioning them. By taking measurements seriously even when they contradicted what seemed obvious. By following the mathematics wherever it led, even when it led somewhere strange. And we figured this out. Humans standing on a small planet orbiting an average star in a typical galaxy used their minds to uncover the deep structure of the cosmos. We measured the unmeasurable. We understood the incomprehensible. We found patterns in nature and described them with equations. We made predictions and tested them. We were right. That's the real story of the speed of light, not just that it's fast. Not just that it's a limit, but that by understanding it, we learn to see the universe as it truly is, not as it appears. We learned that our intuitions about space and time are wrong, and we replaced them with something better, testable, predictive, mathematical truth. This is what separates science from other ways of knowing. We don't just speculate. We don't just philosophize. We measure. We test, we predict. When reality contradicts our expectations, we change our expectations, not reality. We follow the evidence. The speed of light forced us to do this. It forced us to abandon comfortable assumptions about space and time. It forced us to accept that the universe is weirder than we thought. And in accepting that weirdness, in embracing the strangeness, we gained something genuine understanding. The speed of light is 199,792,458 meters per second. But it's also much more than that. It's the key that unlocked spacetime. It's the thread that, when pulled, unraveled our assumptions about reality and revealed something far more magnificent underneath. It's proof that nature has secrets, but those secrets can be discovered. It's evidence that the universe makes sense, even when that sense defies common sense. And the avalanche continues. We're still discovering, still testing, still learning for 100 years in, and we're still accelerating. The speed of light led us to special relativity, then general relativity, then quantum field theory, then our modern understanding of particles and forces and the Big Bang itself. Every answer raises new questions, ever. Why solved mystery reveals deeper mysteries. We now know that space is expanding, that time began, that black holes exist where gravity becomes so strong that not even light can escape. We know that empty space isn't empty, it seethes with quantum fluctuations. We know that mass and energy curve spacetime, creating what we experience as gravity. All of this connects back to the speed of light, gravity. Waves ripple through spacetime at the speed of light. The expansion of space can make distant galaxies recede faster than light, not through space, but because space itself is expanding. Black holes have event horizons defined by the speed of light. Inside the horizon, even light can't escape, and that's exactly how it should be. The universe rewards curiosity. It rewards careful thinking. It rewards those who look closely, measure precisely, and follow the evidence. The universe is both knowable and astonishing, both comprehensible and profound. That's why the speed of light matters. Not because it's a fact to memorize, but because it's a doorway to understanding everything. It's a reminder that reality is deeper than appearance, that truth is worth seeking, that understanding is possible even when the truth is strange. We live in a universe where time can slow down, where space can contract, where causality has a speed limit, where photons experience no time. This is real. This is how things actually are. And we know this because we looked, we measured, we thought, we tested. We did science. The speed of light is not just physics. It's philosophy. It's epistemology. It's a statement about what we can know and how we can know it. It's proof that human reason, combined with careful observation, can uncover truths about nature that are far from obvious. It's evidence that we're not trapped in our immediate sensory experience. We can go deeper. We can understand more. And we're not done. There are still mysteries. We don't fully understand quantum mechanics. We don't know how to unite quantum theory with general relativity. We don't know what dark matter is or what dark energy is. We don't know if there are other universes. We don't know the ultimate fate of our universe, but we're working on it. The same process that revealed the speed of light's true nature observation, hypothesis, prediction, testing continues, the avalanche that started with Newton and Galileo rolls on. Each generation stands on the shoulders of the previous one and sees a little farther. The speed of light showed us the way. It showed us that reality has layers, that surface appearances can deceive, that truth is worth pursuing even when it's counterintuitive, that mathematics can describe nature with stunning precision, that prediction is possible, that understanding is achievable. 300,000 kilometers per second, roughly. The cosmic speed limit, the rate of causality, the conversion factor between space and time, the maximum speed through spacetime, the speed at which massless particles must travel, the barrier that nothing with mass can cross. But more than any of that, proof that the universe makes sense, proof that we can understand it, proof that science works, proof that reality, however strange, is knowable. That's the real meaning of the speed of light. That's why it matters. That's why it's beautiful.